I'd like to introduce Khalid Ahmed from the Platform Computing Group.
Thank you. Thank you, Amanda. So I'll have my 15 minutes of fame on YouTube one of these days. OK, great. Thanks for coming out here, and thanks for Google to put on this conference. So what I'll be talking about is scalability in the context of grid computing, giving you a little bit of background into platform and our products and architecture and how it works, and then talking about some experiments and scenarios that we did in some large-scale clusters, and show how we address some of the bottlenecks that we found and how we're kind of going forward in terms of supporting these large-scale distributed computing infrastructures. So just a bit about platform. Probably a lot of you have not heard of who Platform is. We're a private software company based out of Toronto, Canada, about 500 people. We've been around for 15 years, working in a number of vertical industries, enabling our customers to deploy out large-scale computing infrastructures. So companies like in electronics, manufacturing, and financial services, who use computers to do a lot of their design work, simulations like chip design, car crash simulations, risk modeling, financial analysis, and so on. They use our software to help manage their distributed infrastructures and enable their applications to run within this virtual supercomputer or virtual computer. Okay. This is just an overview of the products that we sell into the market. Basically, what we provide is a layer of workload management software that allows you to run different types of applications, whether they be batch or service-oriented high-performance computing applications and so on a common set of resources. We support a variety of OSs and platforms, integrating them into a sort of a heterogeneous resource pool. So the main products that we sell in the market are our LSF family of products that deal with batch types of workload, primarily used in electronics and manufacturing industries. Our Symphony middleware, which is oriented at high-performance computing in a financial services context, where you have a bunch of services that need to be provisioned and started up, and a messaging layer allowing you to send tasks to these services and do the computations and so on around that. We have a number of other products that we're also selling in the market and embedding our technologies in other applications. So for example, we have an arrangement with SAS that uses some of our grid computing software within their BI analysis and those kinds of tools. So underlying the products that we sell is basically a common technology platform that we call the Enterprise Grid Orchestrator. That's more of a marketing term. But, and this is what I'm going to be talking about primarily today, and talk a little bit about how we use this Enterprise Grid Orchestrator layer within the LSF and Symphony product family. Okay. So let me just give you an idea of the kind of approach that we've evolved to over the years in working with a variety of customers in different industries, right? So we see there's a need for there's all different types of applications within these customer environments. You have the traditional batch types of parallel computations. You have more of the service-oriented applications. You have J2EE and so on, right? There's all these different types of middleware. And what we need to do is provide a way of getting those applications to run within a common infrastructure, a shared infrastructure. So our approach is really to look at all these devices, the nodes within the environment, as basically an anonymous collection of server, CPUs, memory, and disk, right? And we treat the OS that runs on those devices as basically a device driver, right? So you're really trying to aggregate all these devices together and create this virtual computer on top of it. And you're using these underlying devices as components, right? So this is very similar to the Google model, right, of disposable computing where these resources can come and go and fail and so on. So in order to address the issue of connecting these resources to the applications on top, we break up the problem of distributed computing into two layers, right? One is a generic resource management layer, right? So the idea is basically to create a meta OS or a grid OS on top of the individual node OSs. And this is, I'm using the term OS in a loose sense, right? But the idea is to aggregate all these machines and be able to monitor them, allocate them, instantiate activities or processes on them. So a lot of the basic primitives that OS provides on one machine, you're looking at trying to extend out onto a large-scale distributed environment. Okay. So beyond that, to connect the applications, what you need is another layer of software that interacts with this generic resource manager that deals with the nuances or the special requirements of each of these different types of applications, right? So we have the notion of a batch workload manager. That's, again, in our LSF context. We have the notion of a SOA or parallel services workload manager in our Symphony product. The idea is that we can enable other types of middleware, such as J2E and message-oriented middleware, or third-party or custom applications, by creating these adapters or workload managers at the next layer up to be able to basically understand the service levels that are associated with that application. What a unit of work is within that application is different across the different applications, right? In a batch job, it's just a process that you launch. In a service-oriented, it might be something, a computational service or a transactional service that you instantiate in some sort of container. So the kinds of work and the way you measure the service levels associated with that work is different. But on top of these different workload managers, you need a common resource management layer, right? So there has to be a single global resource manager that is able to see the workloads or the requests from different types of applications and is able to make arbitration decisions about what to allocate to what application, how to handle things like failover, right? If a node goes down, how do I recover from that? How do I relaunch processes on other machines and so on? So all those kinds of common capabilities that you see as being needed across different types of applications and middleware, we try to encapsulate that into that resource management layer, right? So the traditional approach has been to build resource management within the workload management. That's the traditional approach. So you do it on a silo, on a per application basis. You build all the capabilities for failover, monitoring, resource detection, and resource allocation within that. But then the issue is that you cannot support, or it's harder to support different types of workloads. Okay, so that's the approach that we're taking. So let me dive down a little bit more, giving you some background into the components, right? Focusing on the resource management layer first. So what's actually installed on the devices and the machines and so on. And this is important to set the context because when I talk about scale, there's bottlenecks within some of these components, and I'll talk about how we address those bottlenecks over time. Okay, so on each of the devices that we manage, there's basically a couple of daemons or low-level agents that are running. One is the LIM, Load Information Manager, and that's basically forms the kind of eyes and ears of the system, right? It monitors the resources, it understands what's available on that resource, what the load state is, static properties such as OS types and versions and all those kinds of things are collected through that. So it's a very lightweight, low overhead data collection mechanism that we have in there, right? The PEM is a process execution manager. That is more the arms and legs in a sense, right? To be able to instantiate and control activities on those bosses, launch processes, control them, monitor them, all those kinds of things. So on top of that, we have this centralized master, right? A master machine that has the LIM and PEM on there as well. And there's an extra couple of daemons on there. So the first is this virtual execution machine kernel daemon. That is basically the allocation service within our software. So that's the component that the other clients go to when they need resources, right? It applies policies on the use of those resources by different applications and allows you to control those according to the various rules that you set. Another component is the service controller. And again, if you use the OS analogy, for a distributed environment, this is the equivalent of the Windows Service Control Manager or initd on the Unix platform. What it does is acts as a bootstrap mechanism for all the other services which will run within the environment. So the other services, again, are things like our session manager and our high-performance computing parallel services, our master batch daemon, which is the batch scheduler, and other components. So the service controller manager basically allows you to define services, ensures that they're always running. If the node fails, it detects that from information that it's gathering from the underlying infrastructure, and it restarts those services and things like that. Okay, so that's the basic component model. Let me give you a little bit of operational overview of how things work within the environment when you have a workload manager running on top of this resource management infrastructure. So our Symfony application or Symfony middleware basically allows you to define or register applications that consist of a set of parallel services, right, within the environment. And one of the components within that middleware is a session manager, right? That's the kind of the central master for a given application. There can be multiple session managers running on an infrastructure, so to support different types of applications. So what the session manager does is basically in response to client requests for processing computations on a grid environment, it will talk to the allocation services of MKD to request resources. So this is the model, again, if you use the OS analogy of a memory manager on an OS and a program doing a malloc call to request memory. Except in this case, we're looking at a distributed set of machines. So we're requesting, give me 500 CPUs with this much memory, with this OS on it, and so on, these attributes on it, to be able to run my computation. So the Ego kernel basically applies a resource policy, a set of resource policies that arbitrates between a set of consumers, right? Consumers of resources that are going to be using that resources, and you define thresholds about how much resource each consumer has access to, and then their ability to potentially share resources between them, right? So one application can say that I need 100 CPUs, but when I'm not using those 100 CPUs, I can lend out those CPUs to somebody else who might need it. Okay, so that's the kernel resource policies. Okay, so then once the resources have been granted, the session manager or any workload manager running on top of this resource management layer then makes use of the execution services. So in the Symfony context, we have components for managing services, that the life cycle of services, a service instance manager down here, and then the actual, oops, okay, going the wrong way. Then the actual services within that. So once that is done, the resource management system basically acts more of a monitoring and control layer after that, so that all the messages begin to flow to the services, the computations are done, and then the results are sent back to services. Now, the system only gets involved when there's a failure, right? So a node goes down, we will inform the session manager about, oh, here's a node that went down. I'm going to give you another node as a substitute in its place, right? It'll tell you when the processes go up and down, if it started or if it exited or if it failed and so on. So it's basically on an exception basis. And then also we get involved when there's a reallocation decision that needs to be made. Let's say another application came in that was of higher priority and needed those resources, so that we reclaim resources from the client that we granted them to. Okay. So that's the basic components in the architecture. What I'm going to focus on next is the way we gather the information, so the LIM, and how that works, right? So we're seeing requirements from a variety of customers to scale the kinds of clusters that we manage to thousands of machines. Today we are able to, in one cluster or one management domain, be able to handle about 5,000 nodes. And we're seeing some requirements especially in financial services, electronics, and so on, that are driving these numbers up quite significantly, right? So today we are at 5,000 nodes, and we're looking at going to, in the next year or so, going to 10,000 nodes with about, if you look at 20K sockets and 40K cores, right, within that environment. And then going even beyond that to 15,000 and 20,000 in the future. So the question arises, how do we scale our infrastructure to be able to deal with these kinds of numbers, right? So not only are the number of machines scaling, but the workloads on those machines are also becoming more complex, right? So you're talking about millions of jobs within the system at any given time. And jobs in the sense can be either sequential jobs running on one machine at a time, or a large parallel computation requiring multiple machines. Okay, so this is where the customers are pushing us towards. And what we were doing in our experiments is to see our basic clustering layer, clustering infrastructure is built around this LIM component, right? So as I mentioned, the LIM basically runs on every node, is able to collect a bunch of performance information. So we have a bunch of metrics that we have out of the box. You have the ability to extend that and add additional metrics, up to 255 dynamic metrics that you can also add that need to be able to be collected on those devices, right? So there's obviously a central master in here, and that, every time you have a central master, you think, okay, that's going to be a bottleneck, right? So how do we address that? As I said, today we have ability to handle 4,000 or 5,000 nodes with one central master, and then we're looking at scaling that beyond that. Okay, so the LIM comes with a set of APIs and so on that allow you to tap in that information. Basically, the master LIM maintains a centralized kind of real-time or near real-time inventory of all the machines and their current load status, right? So you know what's going on in those machines from a memory, CPU utilization, run queue lengths, and all those kinds of metrics from that perspective. So here's just a little bit of a screenshot of being able to take that information from the master LIM, right? So one central point where you can query 5,000 nodes and push that into a kind of more real-time monitoring console. So we integrated with a open source technology that allows you to do the graphing and charting and all those kinds of things. So let me drill into a little bit more into the architecture of the LIM. It's a relatively simple component. It's all written in C, and most of our technology at the resource management layer is in C in order to be optimized and so on. So the LIM basically keeps a in-memory database of cluster information, host information, and other types of resource information. And what happens, it's basically there's a information collection component that periodically gathers information from the OS by either using API calls into the OS layer and into the OS kernel, or potentially by, if you're getting external load information, by invoking commands or whatnot to get that. So the other component is basically information distribution mechanism. So we have collection capabilities on all those nodes. And then we have protocols to allow you to centralize that, right? So we publish that information back to the master node so that clients can query it and make decisions about what's going on. Okay. And underlying that, there's basically a communication channel, just based on TCP and UDP. So we have a lightweight library that wraps around these services to abstract away some of the details about connection management and those kinds of things. So through the channel mechanisms, we communicate with other LIMs or communicate with clients and so on. Okay, so let me talk a little bit about the protocols within the LIM, how they communicate with each other. So basically, because we're using using this to get basic information about the nodes, whether it's up or down, whether it's availability, and so on, we decided very early on to use a very lightweight UDP protocol. So when a LIM comes up, there's one of them is elected as the master. So there's an election algorithm to handle that. I won't go into too many details about that, just because of time. But one of them becomes the master, and he sends out master announcements. So these are UDP packets, very small packets, on the order of a few dozen bytes, that announces itself to the other slaves. The slaves register themselves by basically sending a confirmation message saying that, okay, here I am, here's my basic static information about OS type and number of CPUs and total memory configuration that I have, right? So that registers itself with the master, and then after that, they periodically send load updates, right? So these are done so we sample every 5 seconds by default, and we can send updates up to every 15 seconds, right, to the master node. So we get a good idea about what's going on in somewhat near time about that. We do some optimizations in here to make sure that if the load hasn't changed very much, you don't send that information, right? But there's the load updates also act as a heartbeat, so that at certain times you have to, within a timeout, you have to send a load update, right? So you see that within an environment, you're going to see a lot of these load updates flowing to the master, right? And the master being able to aggregate all these and collect these and publish them to clients that need it. Okay. So this is the basic single cluster mechanism, right? What we have in terms of protocols is also the ability for 2 clusters that are independent to communicate with each other and exchange information as well at that level. So this is the multi-cluster type of technology that we've actually had for quite a while as a base protocol that enabled 2 clusters to communicate with each other and exchange load information about each other so that they can make, again, decisions either for monitoring purposes or scheduling and resource allocation. So what happens in this model is that there's basically some protocol messages to allow you to discover who the master is on the other cluster. So one of the bootstrap mechanisms that you need is that each cluster has to be configured to know at least some of the nodes, right? It doesn't matter which ones they are, at least some of the nodes within the other cluster, so that it can query them and say, who's your master? So then it dynamically locates the master, establishes some synchronization information between the master so that they know what machines there are within that cluster and what their basic information is, right? And then on top of that, so what happens is that we establish TCP connections between the masters, and then we do load information exchange between them. But unlike the single cluster case where each node is publishing information to the master periodically, we do this load exchange on demand, right? So if a client on one cluster needs to know the information on the other cluster, it will query that cluster and get that information over a TCP connection, right? And that TCP connection is maintained over the lifetime of the two. If it drops, then we reconnect and so on. So we want basically a low latency mechanism because the amount of information that is going between clusters is much larger than from a node to the master on one cluster. Okay. So, there's some more details about that, how we do some of the load information. There's a bunch of techniques that we use to make that efficient and scalable within those clusters. Okay. So let me talk a little bit about some experiments we did up at CERN. I mean, trying to address scalability issues when we're relatively small software company. We don't have the infrastructure of Google. We have to rely on our customers to be able to work with us and so on to enable us access. So CERN is a long-term LSF customer of ours. They have access to a fairly large cluster, at least in that context, about 7,000 CPUs, close to 3,000 physical hosts. And what we did was to allow us to simulate much larger clusters than what is physically available. We have this what we call our own kind of virtualization technique, where we can run multiple limbs on a machine and simulate the effect of multiple hosts within that cluster, so that we can simulate 20K, 10K, 20K types of physical machines, because the bottleneck is going to be around the master, not on the slaves, right? So the master configuration that we had, basically a dual core or a quad core machine with 2 CPUs, 16 gigabytes of memory. And what we did was, we were using a variety of, basic low-level tools to basically measure what the bottlenecks are around the master and what we can do to potentially alleviate them. Okay, so this was actually experiments that we did a few years back when we were trying to get to that 5,000 number, and we did some optimizations that I'll talk about. And then going forward, what we're trying to think we're going to do for much larger clusters, right? So actually, it turns out that this is for a 3,000 host cluster, right? It turns out, and this is measuring the actual number of messages or per second that are going to the master, right, from the machines. Oops. What actually happens is that there's a peak that occurs at initialization. That's where the bottleneck actually is. When the cluster first comes up, and it sends out all these announcement messages, right, to a 5,000 node cluster, a lot of those packets get dropped, right, by the OS itself. The network is not actually a bottleneck. It actually delivers all these messages to all those nodes, and all those nodes actually receive it, and then they send back messages quickly, right, to initialize, and then you get kind of a flood of messages that the master cannot handle. At steady state, it's relatively okay in terms of the number of messages per second. The master limb is able to process all those messages and update the in-memory data structures and so on. So it's really the initialization period that happens either when you're starting up the cluster or when there's a failover. That's a bottleneck. So there's actually a fairly slow restart time where the master reconnects with all the machines and gets their load state and so on again. So it takes, on a 5,000 node cluster, it took about 35 minutes for everything to kind of start to sync up again, right? Where you get most of the hosts becoming available and so on. And then the peak loads within those are listed here, right? So as you see that, typically this is going to overflow the default UDP kind of buffer sizes within the OS. Although we can increase them, we found that there's actually better ways of handling that. Okay, so this was kind of the first bottleneck that we faced a few years back, and we looked at a variety of solutions, right? So as I mentioned that, we can handle the steady state behavior, but it's the peak loads that give us the trouble, right? And you get into a situation where you're receiving messages from the previous master limb that was running, and they have to be discarded basically, right? So having the software already running in production and being used in a given environment, we considered various options, right? One of them was to, change the protocols, right, so that we don't have to send as many messages and that kind of thing. Of course, that has an impact on stability and behavior and so on, what customers expect. So we didn't do that. What we looked, some of the other options, things like multi-threading, we considered. Again, because we run on a variety of platforms and that kind of thing. So we decided to kind of avoid that for now, right? And if you look at some of the other really highly scalable event processing software, like the complex event processing engines and so on, they don't generally multi-thread, because then multi-thread also has its own overhead in terms of synchronization and conflict between the threads and all that, right? So we actually took a conservative approach. And we said, the problem is that we're sending out too much information too quickly, right? And if we just distribute the master announcements and the configuration updates and so on over a longer period of time, we would avoid all the buffer overflows that normally occur, right? So that's actually what we did. So initially, we were sending the master announcements, the initialization protocol over, trying to get all that synchronized within 1 minute, right? And therefore, exchanging a lot of messages within that period of time. So what we did, basically, relaxed that, right? So by not trying to do so much, you actually get more done in a shorter period of time, right? So that's the basic premises. So we reduced the packet exchange interval at initialization. And then what we're doing going forward is to look at the, ultimately one master is not going to scale, right? At some point, it's too much for one process, one machine to handle. It's like putting all your eggs in one basket, right? So the obvious thing is to go to a multi-master type of configuration. So this is where we're going to leverage the capabilities we have in our multi-cluster protocol. So that basically you divide up the machines into subclusters, where each subcluster may be, one subnet, or one machine room, or one data center within a site, right? So each of those, so you can have multiple subclusters within the environment, each running a master limb, receiving the load updates from that master, so that it makes it available. Then we would use our multi-cluster protocols, which actually exist today, right, and actually running in productions, to do more of a peer-to-peer type of clustering, right? To use that capability in a hierarchical manner, so we basically have another level of master on top of that, right? So basically a master-master limb that would, in effect, run a one-host kind of cluster, right? That aggregates the information from the submasters and allows that information to be used and published to clients so that they can make decisions on what's going on within the environment. Okay, so we actually did some experiments in that configuration, again, back at CERN. And we went try to get, before we found that at 5K nodes, it was about 35 minutes of initialization time. We bumped it up to 10K nodes, right, with the relaxed message exchange and initialization. And we found that we could get the initialization time, from, if you look at down here when the cluster kind of starts up, to over here when most of the nodes have joined the cluster. It takes about 12 minutes on 10,000 nodes, right? And what we did was, again, using the simulation facilities that we had at CERN, was to see how we go up to 20K, right? So we created 2 subclusters, each with 10K, and measured the initialization time of all the packet exchange and so on that's occurring within those. And we found that, thanks to the parallelism that occurs within that environment when you have 2 subclusters coming up at the same time, that 20,000 nodes is about 15 minutes for initialization. Okay, so that's probably okay, right, for the kinds of environments that we're targeting and the kinds of availability and so on that we need. Okay. So this other diagram here shows the response time to the master limb, the top level master, to requests, right, for load information. So you're making a request for 20,000, give me all the load on 20,000 machines, right? And we can get that, I mean, it's fairly, because we're using lightweight binary protocols and so on. It takes about half a second to fetch information from 20,000 machines across this environment, right? And steady state, initially, there's some peaks at various times, basically when we're leveraging the multi-cluster, so it's kind of doing it on demand. So as the load request comes in, we cache the information for a little while and then fetch it again if it's out of date, right? So that's where some of these peaks come in. Okay, so that's the approach that we are using at the host level to basically aggregate a bunch of hosts and know the state of all the machines within that environment. So the next thing on top of the limb I mentioned is this allocation service. So let me talk a little bit about that and how we are architecting that and trying to get that to scale as well, right? So the allocation service is basically a component that runs on the master node that takes requests from clients to basically allocate me a set of nodes in order to run my work. The clients can, when they're done with the nodes, they can release them back into the pool, or the allocation service can reclaim them at various times. So we've architected this allocation service to be able to have a plug-in model. So it's kind of a framework that allows you to plug in different types of resources within the environment. So our default approach is to use the information that we have from our own information collection service, the Load Information Manager. But theoretically, it can be plugged into anything because it's any other load information collection service that's out there can also be used to gather that information and publish it into this VMKD. We have a generic resource model, so we also are able to deal with other resource types beyond just servers. So things potentially like storage and networking, being able to consider those as factors in the scheduling decisions. So the allocation service basically operates on this notion of a consumer tree, right? The consumer tree is basically just a hierarchical division of the users of the resources, right? So all the different applications that can potentially use those resources can be organized similar to the way you might do an LDAP, okay, organizational structure, right? So if you're an investment bank, you might have or a bank, you might have a investment banking decision, a retail banking group. Within those, you have different applications and sub-applications and so on. So what the policy engine basically does is allows you to set thresholds about things like what each unit owns in terms of number of CPUs, how much they're willing to share within those, if there's any limits within those environments, how much they can use up to, right? So it's doing this in a distributed environment, looking at all the resources that we're getting from the master limb and making those scheduling decisions. So the scheduling algorithms themselves are also plugins so that we can change these algorithms to suit different needs in different industries, right? Different approaches to doing the allocation that might arise. Okay, so putting all this together within this resource management layer, right? You're going to have basically multiple subclusters with a master limb on top of it, a centralized allocation service that's doing sort of bulk allocation or coarse-grained allocation of resources within the environment, and then multiple different workload managers dealing with batch services, J2E, or what have you, requesting resources from this coarse-grained allocation service, and then using those resources to run whatever workload there is within that environment. Okay. So that's from the information side and the allocation side. Then when you get down into the execution side, we're also building out this hierarchy among the execution agents so that the process execution managers within those, rather than one client talking to all of these services individually to start, if you need 5,000 nodes to run a computation, you don't necessarily want to make 5,000 connections from the client to all these nodes. You want to kind of distribute that. So there's going to be a hierarchy within these execution managers, so you have basically a broker at every level that allows you to localize these things within the environment. So you might do this localization either for scalability, or if you want to control the network traffic. So some of these might be in different sites, right? Different locations, so that you can only go through, let's say, certain ports, certain firewalls, and so on. So you can isolate the incoming connections and the outgoing connections to these. Okay. So this is the approach that we've come across based on the experiences that we've had, both experiments that we've done and real-world customer situations where we've kind of looked at the bottlenecks and so on and understood what's going on. Okay, so this is basically, I'll give you a summary at the host level, host scalability level, and maybe I can take a few questions if there are any, and then I'll dive into the workload management aspects of the scalability situation that we've done. So at the information collection level, we found that it's a good combination to use UDP for this dynamic load kind of information, where the latency and the updates are fairly frequent, and you want a lightweight protocol, and then use TCP between kind of clusters or between submasters and the master-master, where you're exchanging a large amount of information. Okay, the whole hierarchical model that we've settled on is the approach that we think allows you to give a single system view of all these distributed resources while still maintaining some locality in the collection, right? We still have the notion of a centralized resource allocation service, because we feel that that's more efficient to do than trying to do a distributed scheduling problem, right? So we do distributed scheduling, but at different layers. So in terms of the coarse-grained resource allocation, all that is centralized, right? And then the fine-grained decision-making about what work unit, what task, and so on to run on what compute node, we delegate that up to the higher-order workload manager, right? So a combination of centralized coarse-grained scheduling and distributed fine-grained scheduling is kind of the approach that we're taking. Okay. Is there any questions at this stage? Okay. Yep.
In your first slide, actually, there are different kinds of target applications that you're focusing on, like compute-intensive or multi-tiered applications. In terms of precise scheduling algorithms or allocation algorithms, how you would allocate in compute-intensive application would be different from a multi-tiered web application, because when you're scheduling, let's say, JDBC database to an app, then it's not just about actually placing your application, but also how you place your data.
Yeah. Yeah. So let me, I forgot to mention that, right? Because I didn't talk much about data, right, within this thing. And data is very important, right? But what we found, again, based on the requirements of the different kinds of application, there's no one data solution that works for every type of application. So if you look in the batch processing in EDA, there's commonly the data infrastructure is NAS, right? Filers that allow you to handle all these, lots of design files. Sometimes they're very small, large numbers of files. In the high-performance computing and financial services, where you're dealing with lots of real-time changes in market data, right? That is coming and going, and you have to reevaluate your risk positions constantly, right? So a lot of computations based on dynamically changing data. The data infrastructure in those kinds of environments is often in-memory caches, right? So different beast than file systems. If you're running MPI types of applications, highly parallel applications, things like the Lustre guys are doing with cluster file systems are the appropriate approach. In the J2E context, databases, right, and SAN storage and so on. So each of these environments are different in the kind of data back end that you need to support that and make best use of that. So we don't dictate that. That's a whole separate area, right? But what we do is integrate with those data storage mechanisms so that when we do the allocation of resources, we're aware of things like data locality, right? We treat data in that sense as a resource. So one of the situations we had in electronic design is that we were able to send out thousands of jobs to all these compute nodes, but what they would do is fetch the design files and hammer the files really, really hard and take them to their knees, right? So then you get into situations where you need to be able to be aware of what the load is on the filers and kind of throttled back, right? Some of the processing that you're doing, right? Ultimately, if you have a infinitely scalable file system or an infinitely scalable filer, then we won't need that, right? But the reality is that there's different bottlenecks within the storage that is triggered by the ability to do all these distributed computations. Okay, I don't know if that answers your question or not, but at a high level, that's kind of for the J2E environments, then it's the databases part. Maybe whether you want to run them on the grid or not is an open question, right? How dynamic you want to make them is another open question. The J2E is probably easier to do at the app server cluster, right? So at the WebLogic or the JBoss, where they're relatively either they're stateless or they have their own clustering mechanism that allow them to synchronize the state in between requests. Okay.
Do you have any data on the overhead of running LIM?
Yeah. So the question was, what is the overhead on the running LIM, right? So our customers always want to use their resources to run their work and not to manage, right? So LIM is very lightweight. It's written in C, and it uses system calls to get all the information by default, right? So you're talking less than 1% CPU overhead, if even that. And then on the network side, it's trivial, right? Again, less than 1%. Maybe about 10, 15 megs in memory on the node. So that's on each slave node. On the master node, obviously, it's a little bit more. Okay. Okay, let me just give you a quick overview of some of the stuff that we're doing on the workload side. I'll go through this a little fast because probably running out of time here as well. So in terms of the workload scalability, our Symphony middleware is, again, a way of parallelizing a single computation, right? So it provides you APIs to decompose your application into services that run on the compute nodes and clients that access those services to do a computation in a kind of a master worker parallel calculation, right? So the components in here I've talked about a little bit before. The main bottleneck in the Symphony environment is this session manager. That's the central point that receives all the messages, right, for doing the computation. It handles the data distribution of those messages to the slave nodes, right, to the compute nodes, and gets the results back and returns them to the client, right? So the requirements in a more real-time kind of environment are around latency and throughput and making sure that we efficiently utilize the resources that are given to us. So we have a variety of techniques that, from thread pooling in the SSM. The SSM is written in C++. It's a multi-threaded application. Because we're doing a lot of I/O, it makes sense to kind of handle that, right, at the communication layer, both disk I/O and network I/O. And so we did some experiments at an IBM lab and their deep computing things to measure the scalability of this messaging middleware. This just gives you a little bit of a diagram of the environment, a whole bunch of racks with Cisco switches and so on. So all these, the yellow ones are all compute nodes. There's some management nodes over here which run our session manager and some of the other components. So we measured things like efficiency, right? CPU efficiency. So even if the resource manager gives you access to 5,000 nodes, can you actually make use of them efficiently? Can you run all your computations? Can you keep all the nodes going at full throttle for all the time, assuming that you have enough tasks to run? Okay. So what we found is that again, this was the latest generation. We had previous experiences where we had scalability bottlenecks and so on around pushing data through the messaging layer. I'll talk about some of the things that we did in terms of optimizing the communication protocols. Originally, we had things using web services and HTTP on the front end. We found those were bottlenecks, right? So we switched over to a binary protocol, lightweight, common data representation and so on, that allows us to transfer these messages. And we got fairly good speed up for tasks that are relatively faster than shorter than you would find in a typical batch environment, on the order of seconds and maybe 30, 40 seconds and so on. So we're able to get good speed up within those environments, fairly almost linear at this point. We have the ability to make persistency within the SSM so that if the client goes away or the services go away, optional, right? So that when the messages are sent to the SSM, you can specify a quality of service that says, I will persist data to disk to handle reliability, or I won't persist data to disk, again, to get the speed up. And obviously, when you don't persist data to disk, you get this kind of speed up, right? Okay. So another measurements that we did was measure kind of round trip time. And again, we found that it's fairly lightweight, about 5 milliseconds latency on some of these computations. And we're able to get that down and so on. So again, basically a summary of the approaches I mentioned. Initially, we had web services and those kinds of protocols. Those don't really scale if you want to get to that level and that kind of latency. So we're using native communication mechanisms and so on, right? Again, a C++ implementation as opposed to a Java implementation. We use a push approach to pushing out the messages rather than having the workers kind of call up to the central session manager and pull work down. We find that that's more controlled, okay? And then, as I mentioned, making the disk operations all efficient by using multi-threading and handling the network I/O through multiple threads and so on. Okay, so that's basically the approach. I'll stop here and take questions because I think we're basically out of time. I do have more slides on our batch experiences, but I can handle that in Q&A afterwards. So any questions or comments and so on? Okay, clear as mud? Sure.
The master limb is not a single point of failure, right? If it dies, then one slave is going to be
Yeah, so the question was, is the master limb a single point of failure? No, it's not, right? So there's, I didn't mention the master election protocols and algorithms that we have, but basically as part of the communication, we detect if the master goes down and one of the slaves basically picks up as the role of the master. So it takes, depending on how you set the thresholds and so on, it can take up to a minute or two for that to happen, right? But you recover all the state and everything continues to work. So when the master goes down, it doesn't affect all the other computations that are already ongoing. So once you've done all the resource allocation decisions and so on, all those computations are continuing to process and not being affected by what's happening at the resource management layer. Question?
You mentioned Java a couple different times, as well as C++ from a development point of view. When you're building the different tasks to be able to feed those through, do you put an integration layer inside of like a JBoss container, or how do you feed the grid?
Yeah, so the question was, how do we feed the grid from Java-based applications? So The answer is that our middleware or the server-side components are written in C, C++, but on the client side, we do provide Java APIs and Java libraries and so on, right? And in terms of the management infrastructure, we have a base C API as well as a web services interface. Again, it's more for control operations, right? Monitoring, troubleshooting, all those things are exposed via web services, so you can access, and we provide Java APIs on top of that, right, to support that. Or you can use Perl, Python, or whatever web services ready language that you have. Okay, any other questions? Okay, great. Thank you very much for your time and patience.